you may start, I mean, you see, all is red here on the single line diagram. That means there is no data. And you find out this is the point of common coupling, the high voltage cables between the entrance of the steel plant to the substation. This is the step-down transformer. Again, high voltage cable to the compensation and to the reactor. Here, this is the second furnace. That can be a melting furnace or ladle furnace. Then capacitor bank and SVC. EAF transformer and high current system. And then the arc. Okay, if you try to make calculation, nothing, yeah? So, either you fill up all the items or you start by read models from somewhere. For example, this one. Yeah? So you see that I put everything so it's green. So if you want to, let's say, modify the data, you click on the item and here you put the main parameters. For example, this is shown here, short circuit power on PCC. It's clear for everybody. Yeah? Nominal voltage of the incoming line, 220 kilovolts. Correction factor, this is between 0.95 and 1.1. This is, let's say, to simulate variations. Yeah? And this I never use. High current cables, if it's installed, you give the resistance and the reactance, it doesn't calculate itself by the length and the feature. Step-down transformer, so the transformer is given by the MVA. You may have several transformers in parallel, but they have to be the same, yeah? Better, otherwise it's not equilibrated. Primary voltage, secondary voltage, ohm losses, and impedance. The furnace transformer is somehow different because you have to give the rated power and the maximum power. Sometimes you have many times you have, let's say, overload allowed for, let's say, the melting phase if you have 20 minutes rest time between two heats. Yeah. So sometimes you have here, let's say, 10 or 20% overload capacity. Primary voltage. Then here, this is the secondary voltage at rated power and primary rated current. That means here you have the maximum voltage. It's a mistake, it should be 613. So usually this is the maximum tap voltage for which the transformer has been designed and for which with the 42 kiloamps and for which the primary current will be at its maximum at 32 MVA.
Is it possible to add the tap? And now it's 13 and 14, 21.
Wait, I will tell you. And the second term is very important as well. 440, this is the transformer tap. At least it should be 470, for example, where the 32 MVA is achieved with the maximum current, secondary. Right? That gives you the area of the constant current, yeah, from 400 to 470, and the area of constant power for 470 down to 630. But of course the current will go down. Alright? It's well known to everybody. Doesn't seem, yeah?
Mm-hmm. It's a the electricians will know.
No, but everybody has to know. Everybody has to know.
Yeah,
Even
yeah.
the process engineer.
Yeah, but till now.
If you don't raise the finger, I cannot imagine. Or it's already too late in the afternoon for you to be okay?
No. 온도 맞춰라. 그 온도 좀 맞춰. 됐다. For the step, the voltage divided. For the step, voltage has divided. I understand.
You understand?
Mr. Bean is genius.
저기 반사돼가지고 글자가 반사된 거 안 보이나? 다른 거 다 그 요거를
So, if you increase the transformer taps, you have here increased power, constant power to the maximum voltage. On the other side, you have here constant current, and here at the same point. Okay? This will give the section of the wires in a transformer, secondary side. Yeah.
Section wire.
The maximum current is giving you more or less the weight of copper you have to put in a transformer. Because if you increase the secondary current, you have to have a bigger diameter to avoid overheating. Yeah? So now everybody knows, yeah? Transformer, constant power area, constant power area, constant current area. Okay. So this is important when you specify transformer to give maximum voltage at rated power, maximum voltage at rated current.
뭐?
Maximum voltage at rated power, maximum voltage at rated current, here. Then impedance in short circuit is also important because low impedance transformers is more expensive. Yeah. And then circuit arrangement, most of the time secondary side is delta. Star is better for the ladle furnace or for small transformer, but for high power furnaces, delta is better. So if you want to increase the number of taps, you just have to change here. Yeah? And you have 2 more taps. Or if you have less, okay. Here you have the status, is it okay or not? And here, this is the value you are allowed to put. This is a real, so you can put comma and stuff like behind. And here is to select. You have only these possibilities. Okay? And then you put the tap. Normally it's supplied by the transformer supplier. Yeah. Transformer reactor. Reactor, you have to give the rated MVA. Normally it should be the same MVA than the transformer, slightly higher. The power and the voltage and the ohms. Here it's not milliohms, it's ohms. Yeah? And the ohm losses. And if you want to have taps, you have to specify the taps here. Okay? So this is ladle furnace, not installed, but you just give, let's say, the power and the reactive power. Capacitor, same, very easy. And the SVC, the power installed, the voltage, and here the start level. It may be that you don't start the SVC if the MVAR is below a certain value. Yeah, so you may specify the start point for the SVC. It's not very, very important. And finally, the secondary bus bar. This is the result of the dip test. Yeah? So when everything is fulfilled, you may select here the transformer tap you want to calculate with the reactor tap, and here, you see this is integer. Here, the way the arc model is selecting, this is more or less equivalent to the F factor what we have seen yesterday for the harmonic content. But in this case, we were just able to simulate the Bowman because the F Bowman is looping on the cosinus phi. Looping, making loops.
Loops,
yeah. And the ESC model, I mean my model, is looping on the current. So it's totally different, let's say, modelization, and they didn't want to spend too much time to program it, which is a mistake because start current, end current, and delta current, number of digits. The comma is already one digit, yeah? So 3 is maybe not enough, but never mind. So you can select here, forming slide. VAI, I don't suggest you to use it because it's very inaccurate. Test is nothing. So Bowman start melting, this is boring phase at the beginning of melting, main melting, and forming slide. This is the 3 cases you have to consider. Huh?
So when we click it, change it step by step.
And you can select all these parameters to be calculated. So here you have the active power, reactive power, and apparent power, power factor, voltage, current. And each point you see you have a B. B is here represented at the arc. H is at the secondary of the transformer. O is primary of the transformer. D is primary of the reactor. So you can select each point here, yeah, everywhere. Additional parameter, K is the stability factor, what we have seen yesterday. This is the arc length. This is the arc resistance. And this is the impedance. The arc radiation, but in this case, the system doesn't know the furnace dimension. Yeah? So you will not get kilowatt volt per square centimeter, you will get only megawatt volt. You will see on the table. I put it here. Then primary current in percentage, secondary current in percentage. So let's have a look on the table. When you click on calc table, you get these results here. And you have the parameters here on top and the value here, the unit. Yeah? For example, primary is in kilovolt, kiloamps, and you see the resistance is megawatt kilovolt. So you have to multiply it by 10 6 to have in kilowatt volt, and then to divide by the square centimeters. You have to calculate yourself. Yeah? This you can select the format you want to export. Yeah? Because you can store this file somewhere. Whatever. And you will receive a text file. Yeah? So it's better to configure it. This is still in German, yeah? This is the where you put the model.
Model
The model is the steel plant. Yeah. This is the output of all the files. Yeah. And this is the set points. I mean the setting. Excuse me. Settings. Mapo Tofu is still surviving. Okay. So this is calculation. Standard, this is to select the parameters. Otherwise, you may remove, let's say, all parameters. If I take standard, it's take again the standard. And you may have a description of all parameters here. Yeah? Yeah? And you may select all. WinWord, if you click this, this is the results. I'm not sure. Shit, it's not in this one. So you see, this is all parameters. Huh?
그렇죠. 지금 에어컨 때 다른 게
Okay.
없지.
In terms of
없나?
yeah,
우리 이런 거
알았어요.
들어와야 되거든.
there is a possibility. So this is for symmetrical calculation. Means each phase is equilibrated. Equilibrated. I mean, each phase has the same settings. But you put a furnace on operation, and after a while you see the phase number 1 is extra worn out.
Extra one.
Yeah, there is too much wear yeah. Or you see that on the measurement from the ECS, the phase number, even if you have the same set point, phase number 1 has a higher arc length because higher voltage. So you can do unsymmetrical calculation. So this is again to select the parameter you want to display on the sheet, and this is the settings how to calculate. So you select the tap, you select the primary voltage, the reactor tap. This is to have a operational reactance. If you have particular conditions with bad reactance, I mean, a lot of flicker you can change, but not necessary. So, phase number A is given in current. Phase number B, that means phase number 2,
different.
you have a range. That means you start with 28 kiloamps, you end up with 33 kiloamps, and you jump by 0.5 kiloamps. And this is the current of phase number 3. And you see you can unbalance the currents. Okay?
So I have a stupid question. The tap, the actual number of tap, yeah, the sum is 5, sum is 10, 15. How to decide it? What is major factor decide
Look.
number of taps?
It's up to you. What you have to know is that the voltage difference between two taps is given by the tap changer supplier. It's in a range of 35 volts. Yeah.
35 volt is
Because otherwise they have the risk
changer.
of internal current circulation in the tap changer. So it's in the range of 35 volts. Afterward, knowing this, you know the maximum tap, and you have to decide for the lowest tap.
Lower stop and the maximum.
Yeah.
And then the
For
each
example,
tap certified voltage.
For a furnace of 150 tons, it would be stupid to have a lower stop at 150 volts. You would select 750, for example, up to 1,200, something like that. When you know this, you know how much tap you have.
Okay.
Yeah. But this is coming by experience. You will make the first project, you will have, let's say, it's more or less standard, plus minus some volts, but not really critical. Yeah? So this is after startup, let's say, yeah? Where you see that after startup, when the network is unbalanced.
Yeah, I see.
Then you have the power diagram. So you select the tap you want to display, and the way Bowman forming slag, boring, refining, and okay. So you have the kiloamps and the megawatts. So with this you can change the parameters. For example, you have, but each time when you make a change, you have to click Übernahmewerte. That means take over the data. Yeah? And when you close, then you have the grid. Yeah? You can put to clipboard, I mean copy in a clipboard, and you can paste in any other document. Yeah? And this is not really working, so don't try. And then you can export in different text format. This is different format possibility. Yeah? DXF, for example, AGL, I don't know what kind of format is it.
Okay.
Yeah? So each time you will see here on top in the title the reactor tab, the plant name here in the common data, and the way it has been calculated here for Mixline. Circle diagram, I never use the circle diagram, but for those who likes it. And you can display, I mean, all these parameters on top of the diagram, you see, the voltage. The cosinus phi constant, this is the blue line. This is the arc length, here in green. This is the maximum primary current, and this is the maximum secondary current. So that means for the lowest step, here, you see that we are working on this line, and then we have to work on this line. This area is giving you the working area of the transformer. Here above is forbidden, here above is forbidden. Then flicker. The flicker, so you have the, you can give the, this is the transformer tap. And here the reactor tap. And you have the PST, giving the KST of the furnace. KST is the harmonic generation from the furnace.
Oh, harmonic generation.
Yeah. So the minimum is 40. No. 45 or 50. Yeah, 50. 50 is considered to be, let's say, the ladle furnace, for example, or foaming slag. And let's say powerful furnace, start of melting, it's about 90. So with this, you know that you have to, what kind of harmonic you can expect with this SVC. Yeah. So 2.2 is much too high. I never use this
그러면은 저다 이해되겠나?
because I'm all the time far above the PST1, so I don't rely so much on this.
정규 그렇죠. 그래.
There were a possibility to store.
저거만 있으면
응?
저게 어차피 세트포인트 일려가는
여기서 아까 얘기하는 임피던스 계산하는 이 안에 들어있으면 더 이상 작동이 안 된다라더라고.
There were a possibility to store the input. Wait a minute. Yeah. With this function here, you will store all the input Eingabe. Okay. Ergebnis, this is result, Eingabe is input. Yeah, and then you have everything. You see? Okay, from the point of common coupling down to the secondary. But take care if you want to print this. I don't remember where is the print preview. You know where is the print preview?
print preview?
Yeah.
I think
It's on the top.
file, P
Ooh.
P
It's on your code. Yeah. No. Left. The small icon.
Small icon. Listen.
You see it here. It's small.
No, this is printer.
preview.
With print preview.
No, right, but yeah, 줘봐. 여기하면 있을까? You click here. Edit the button, commanders, and
Yeah.
네, 저 있네요. 5번째 있네요. 5번째. 올라가.
그러면
Up.
5번째.
No, just 그냥
Okay. Then I have everything.
just put it show there. Preview P.
No, it's I. Imprimé.
I? No. Yeah, we find it.
Oh, it's here.
Okay.
Oh.
Good.
So I'll do it differently.
Test.
Because there is a trick. Yeah? You see? Here. Eh?
Really?
Yeah. So you just see it when you print it. Even on the print preview, it's not visible.
Okay, I will.
So take care.
No, I will try delete.
Yeah. And you see there is still some German even if... Okay. So you have to manipulate and make tries and errors. Yeah.
And you said to me the impedance calculation program is not running in here.
There is no interface to activate the impedance calculation.
Okay. And please show the okay. That's it. That's it.
But in the other program, so this is the main program. You see, you have electrical yeah, symmetrische Größen. This one is doing the same calculation that what we have seen. Oops. Ah.
One more time.
So you put all the, you see, all the single line diagram features. Normally they should be the same denomination than on the other one. Yeah? And then calculation, but it doesn't work. And I don't know why. Maybe your genius programmer will know. I think it's a question of incompatibility between DOS and Windows 7. Because it used to work before with XP.
No.